All right, and welcome back, everyone. So we are done with our introduction. We've set up just about everything we need to in order to start tackling the question of how to compute solutions to differential equations. And remember, our first goal here is to start low, so start with low complexity, and start building toward more complex solutions, more complicated and sophisticated equations. So we are going to begin with what is generally regarded as one of the simplest types of differential equations, and these are the first order differential equations. Remember, these are the guys that only ever involve the first derivative of a function, right? Nothing else, nothing more, nothing less. So let's go ahead and get started. What I'd like to start with is just kind of an introduction to the first type, like the easiest type of differential equation that we can solve in first order. And that would be stuff of this form here, where we're looking at a function of t, y, y prime that takes this form. And in particular, if I draw on the notes over on this page, a of t times y prime plus b of t times y plus some function of t is going to be 0. This is the general form that we're going to be taking for a first order linear equation, right? So first order linear ODE. Oh, ODE? No, just a capital ODE. There we go. First order linear ODE. Now, the thing that makes this linear is the fact that every time we see an instance of y or y prime in the equation, there's no power associated with it. There's no sine function. There's no log, no nothing here. And the reason why we like that is if we make the following substitution, right? If you saw the classification video, then you can go ahead and skip this part. But the idea is that y prime then, if I were to put in a sum of functions here, this would be u prime plus v prime. So a of t, and oh, by the way, we remember if we're going to do this correctly and showcase the right thing, okay, we're not actually going to erase that, but we are going to say let g of t just be a function of y and y prime, and that will be this function, just the pieces that involve the y and the y prime from the equation upstairs, right? Then what's going to happen here? If I substitute u plus v and u plus v prime into this equation, then what I wind up with is a of t times u prime plus v prime plus b of t times u plus v. And what I can wind up doing here is split this up so that I only see, I'm going to drop the function of t notation, plus a v prime. So there's the first bit. And the second allows me to distribute the b across the sum u plus v. And then I can go ahead and regroup these guys solely in terms of u's and v's. So wind up with a v prime plus a bv, and then lo and behold, this is what happens when I substitute u and v individually into this function. Right, and this is just one half of the definition of linearity. So we can also note that g of, and we'll do lambda u and then the derivative of lambda u, is actually going to be exactly the same thing as me just factoring out that lambda from the g function. So these two things together, the fact that I can split across sums and I can factor out constants or scalars, is what makes this equation linear. Okay, that was it. So notice I'm ignoring the fact that a and b and c are all functions of t and can be nonlinear themselves. The thing that really that we really want to pay attention to is what's happening in the dependent variable, in the function that we're trying to solve for and its derivatives. Those are the pieces that are going to be deemed linear. So notice that there's kind of a little bit of wiggle room in how we describe this equation. This is not the only way that I could write down this equation. In fact, I could multiply this by any scalar, right? So multiply by 2 on both sides. Or I could multiply by any function on either side. So I don't know, I can do maybe a d function, d of t multiplied by on both sides. And I'd still have an equivalent, an algebraically equivalent equation for this differential equation. So what I need to do in the first place is kind of guarantee a standard form, just telling ourselves that there are many different ways that we can express this equation, but that there should be one that we really pay attention to as far as the theory is concerned. So we're not going to go after this function but so much as we're going to go ahead and create a standard form for this equation, and that's this dy dt term that is unaccompanied by any variable coefficient. So there's no a of t term sitting in front of the y prime anymore, and we can get there just by dividing this equation through by a of t. Right? So if we need to put this in a standard form, then we can. Any first order linear equation then will take this form, right, that I just erased and am redrawing, right? That guy is what we're going to call the first order linear ODE, or the linear first order, whatever you want to call him. This is the standard form of the object that we're trying to study. Right. So why do we want to put this guy in this particular form? Well, let me see if I can't convince you that this is a good idea. This left-hand side of the equation, dy dt plus p of t times y. If you've taken first semester, first quarter calculus, differential calculus, this should look very familiar to you. Maybe not in this particular form, but it should look familiar, that there's a sum of this function y with some multiple on it, and then there's also, we're adding on to it this derivative of y. So this is vaguely reminiscent of a product rule, right? So remember the product rule? I remember the product rule. Do you remember the product rule? U times v prime is equal to u prime v plus u v prime. So notice that we are differentiating on each term in the product and then summing over all the different derivatives that we could compute. So what we would like to do here is say that this guy, this expression on the left-hand side of the differential equation, is the product rule for some function, or for, let's say, mu y, right? It should look like the derivative of this product. And what we would hopefully like to do, what we could hopefully do with this, is just say that there is some function mu that I can multiply into this, so mu times dy dt plus p of t times y, and with any luck, that should just equal the product rule for mu times y, given the appropriate choice of mu. So let's see what this actually looks like. If we were to make this assumption that there was a function mu that would make this work, let's see what happens. And I'm going to go ahead and drop my my Leibniz notation here, because it's a little cumbersome to deal with on the fly. So with the prime notation here, notice that the right-hand side, so I'm distributing this mu across the sum on the left-hand side, and I'm expanding out what the product rule looks like on the right-hand side. And immediately we notice that there's a mu y prime common to both sides. So both of those guys can go away, right? We can just subtract them off of both sides, which would leave us with mu times py is equal to mu prime y. Okay, now, before you say, oh yeah, just divide through by y, what happens if y is equal to 0? Yeah, then this equation is satisfied. So I do need to be careful that I'm not just going to go ahead and divide through by something that could equal 0. So what I'm going to do instead is bring this other piece, this mu prime y, over to the left-hand side so that I have a 0 on the right. And what I can do at this point is factor. And I'll factor out on the left-hand side, I will factor out this y. So this implies that either y is equal to the 0 function, so that triple equals means identically equal to, right? Identically equal to the 0 function. I'll put that in quotes, that's how you should read it. Or this mu times p minus mu prime needs to be identically the zero function. So I think it's pretty clear that this y is identically equal to 0 could actually work for some class of these equations, for some... Oh, did I even write the whole thing down? I didn't write the standard form down, shame on me. So the standard form is up here, so y prime plus py equals q. Right, so so y equals 0 is only ever going to solve this equation if this q piece goes away. So if the q term on the right-hand side vanishes, if this is a homogeneous linear equation. So this is possible, but not always true, that y is identically the zero function. So what I need to do is actually consider what happens in the general setting where I satisfy this, right? Where this mu is the thing that I have control over. And notice, if I rewrite this, d mu dt, p dt, and then d mu over mu, well, look at that, it separates. So if I integrate both sides, then lo and behold, I wind up with the natural log of mu plus some constant is equal to, well, I'm going to put the constant on the other side because that's where my independent variable is. Then this will be, well, I really don't know what this function will be, but it is going to get a plus c associated with it. I don't know what the antiderivative of p is. I'm just going to leave it as a placeholder for right now. So if I do this, notice that I don't need to figure this out for every choice of mu or every possible mu. I just need to make sure this works for some mu. And in this case, that justifies me setting the c equal to 0. I just need to make this work for some function. It doesn't have to work for an infinite family of functions, but it does need to work for one. And the way that I'm going to finish this off is by solving for the mu here. We've already seen what we can do in this case. So mu of t will have to be the exponential of the antiderivative of this p function. And this is what we call an integrating factor. Right? And this is the function that if I multiply it into this equation, then let's see, so it'd be y prime plus py equals q down here. If I multiply through by a mu py is mu q, then by design, this left-hand side, I'm not doing anything funky here, I'm just rewriting that this on the left-hand side is the product rule when I use this integrating factor. When I multiply both sides of the equation by a p, the left-hand side looks like the product rule for mu times y. So what happens if I then integrate this? Well, then have a look. The integral of a derivative, you'll remember, is canceled. Well, there's an additive constant here, but notice that I still just get this mu times q dt on the right-hand side, but that means that I can actually solve for the y now, and this will be 1 over mu t, integrate mu of t, q of t, dt. And ladies and gentlemen, I'll hold for your applause. This is the complete general solution, right? This is the complete general solution for first order linear ODEs. And that's it. That's the entire story. We know exactly how to solve every single one of these kind of ODE. And I even have that at the bottom of the lecture notes here. So indeed, there is just this one way to solve, or that there is a way to solve these equations. And in the next video, we'll go through a couple of examples to see exactly how this works, but this video is just about the derivation of this form. And remember, this mu that we derived here, this is called an integrating factor, and it is very specific to the fact that we're using the standard form of this ODE. So be very careful that you have a 1 sitting in front of this y prime before you start computing this integrating factor. Your work will not work otherwise.